So they have logic. They have also limited logical reasoning. So, for example, there is Terry Tao, which is who is like a very strong mathematician, and he tried, the last version of GPT, and he said basically, they are actually very limited. Again, you need to give them a lot of precise prompt to make it work. So they have a limited logical reasoning. So what OpenAI tried recently to do is to improve that by learning, chain of thoughts, for example, and also for inference to do search algorithms. So it improves this limitation, but it's still not there. They have also limited graph reasoning capabilities, even, again, if they have seen the test set of the graph task during training. For GNNs, I think the strength is basically to be able, so if you have a graph like this and you have a question, for example, is the Mona Lisa in the same city as Alice's friend Bob? So you have here Mona Lisa, you have the city, you have Alice, you have Bob. So if you do multiple layers of GNN, what you will do, you will basically learn a multi-hop path that will go through the solution of your task. So they are very good to do that, and they are very effective for many different modalities. And now we're talking about text, but they are also very good for example, physics, biology, combinatorial optimization, and also chemistry. And we know that chemistry, that was the very good year for AI. So there was a Nobel Prize in chemistry for AlphaFold, and AlphaFold, as you know, is an edge transformer. So predicting the pairwise distances between residues in amino acid sequences. So this is a graph neural network, basically. Limitations for GNNs is basically they like graph foundation model in the scale of natural language processing and computer vision. Of course, the community has worked a lot on that. It's very interesting to push in this direction, but there is this emergent property. Basically means that we need to go beyond the scale of training data and compute to get something very powerful. So we are not yet there. The problem is basically, the data set. We don't have like large data set available. OGB, is still comparatively small compared to ImageNet, which has 150 gigabytes of images. The hardware for running sparse linear algebra is not optimized. It's much slower than standard dense operations. Existing pre-trained GNNs, because basically of that, they are small. They are not doing billions of parameters. This is basically millions of parameters. And I think also something which is today, which is a limitation, is that industry has not yet found some interesting application of GNN, because industry is really driven, the AI research and AI product. Why we have GPT today, it's because industry got interested in deep learning, and then also to develop, product. So it's not yet clear, how to make profitable stuff from GNNs. It will come, I think, but it's not yet there. So combining LLM and GNNs, basically, it means developing training a joint text and graph foundation model. And this is, of course, a very attractive idea, very promising idea. But today, I think the issue is that there is a very huge imbalance between the knowledge coming from text, from LLMs, and the knowledge coming from GNN. So, of course, what we would like to do is to do this kind, of architecture where we have the text, then the text will go through an LLM, it will process it, it will give us some vectors. The same also for graph, it will go to the GNN, we'll process it, will give us some vector, and then the vectors will be processed together with self-attention or cross-attention, and for example, if we do text generation. So the fact that we have a huge difference between these two domains, I think this is very challenging. So what it means basically that we need to tailor, the combination of LLMs and GNNs to get some value of that. So, for example, what we can do, we can use the LLM using the vast knowledge of LLM, and then try to improve the performance of small-scale text attributed graphs. And we can also do the reverse one, that we can use a knowledge graph, for example, to constrain the LLM to give more precise response. Okay, so reducing hallucinations this way. So this is what we will do next. So we will review two works that we have done, and this is really focusing on text reasoning task. So the first work will be we will use LLMs to enhance GNN reasoning. So this is a work basically that is taking LLM reasoning abilities to improve GNN predictions, and it's pretty actually effective and robust. The second paper we will review is basically a GNN will enhance LLM reasoning. So this is a foundation work where we try to put together all the benefits of LLMs, GNNs, and also something that we call graph RAG that I will explain. Okay, so let's see the first technique here. So the technique is called tape. So here the idea would be to use LLM knowledge to improve the quality of the node features in a tag. Okay, so if we have better node feature, then we will be able to predict, with more accuracy, with higher accuracy. So the question is, how do we extract again information from an LLM for a specific tag task? So to do that, we are going to prompt the LLM, because LLM are again accumulated so much knowledge that what we would like to do is to prompt the prediction of the LLM, but at the same time, we also want to understand its reasoning. Okay, so we will ask so given, for example, an article, the article would be the title, the abstract. We will ask the prompt question, so basically predict the class. But at the same time, we will ask the LLM to give us, its reasoning. So why did you decide for these predictions? Okay, so we call also reasoning or explanation if you want. Okay. So now that we have the sequence of words for abstract, title, explanation, prediction, this is not something that we can directly use with GNNs. So what we need to do basically is to have a mapping from sequence to vector. Okay, so we want to take this input sequence of words and then output a d-dimensional vector that will summarize this information and that will improve basically the expressivity of this node feature. So remember that in this example, a node is an article. Okay, this is another article, and then what we want is to predict if there is a relationship. No, I'm sorry. And what we want to predict is, the class. Okay. So what we propose something that is going to leverage both proprietary and open source LLMs. So this technique is a kind of interpreter between a closed LLM and an open LLM. Okay, so the closed LLM can be GPT, that can be Gemini. So we know that these proprietary LLMs actually are better than the open ones. Okay, so we can go on the leaderboard of LLMs, and you see that always the top two are GPT and Gemini. Okay, so unfortunately for researcher, proprietary LLMs, they are better than the open ones. But the problem with the closed LLMs is basically that they only provide sequence of words, right? They don't provide the vectors that we want to train the GNN. So in contrast, if you look at the open source LLMs like Llama or Gima, basically they are going to provide the text, but also the vectors, right? So we have access to everything inside the architecture. We have the hidden vectors, the hidden features, but also the output. Everything is given to us. So what we decided to do in 2022, so at that time, GPT 3.5 was the best closed LLM. So this is the one that we used. So we have our article. So this is the node I in the graph. Given the title, the abstract, we query, we get the explanation, we get the prediction. And then what we do is that we are going to convert the sequence of, for example, of words in the prediction by using a a language model, so like a small one, which is DBERTA in this situation. It has 129 million parameters. And here, let me zoom in. So what we do is basically, so we have our sequence of word tokens. So this is basically the explanation if you want. And here we have, in any transformer architecture, you can have a class token, basically, something that will summarize the sequence of words. So we give as an input this, we go through L transformer layers, we output, and then we get the class token after L number of transformer. Then we go through an MLP, a small MLP, to fine-tune on the training set. Okay, so the training set, we know the correct class. So we want basically to fine-tune the MLP on the correct class of the training set. So in the MLP here, it's a small one, only 2 layers. The first layer basically will just be some features, and then it will go through another layers to get the number of classes. So for example, that can be 40, 7 if it is Cora, 40 if it is OGB archive. So this guy here is going to be a vector of 700 dimensions. So this is actually going to be our enriched feature. So this feature will represent the input sequence that we have here. Okay, and this is very tailored to the task that you want to solve. Okay, so this way we are able to get enriched feature for the explanations, enriched feature for title abstract, and then we can also have prediction feature. Okay, so what we should do if we are in 2024, actually we should change the small DBERTA language model by now using a large language model. Okay, so why we can do that at the university is basically if you take, for example, Llama 2 or GMA, you can fine-tune them using this very nice technique of LoRa. Okay, so low rank fine-tuning. And basically with my small GPUs, actually I'm able to fine-tune a large language model like Llama 2. So this is very great. Okay, so basically what we will do, we just need to change the proprietary LLM with the best one. So you take the one that you like. And then here, instead of using the DBERTA, you can use Llama 2, for example. Okay, so once you have your enriched node features, what you're going to do, you are going to train your GNN, okay, with these new node features. So you can use your favorite GNN, okay, and then you can make the prediction. So we can compare the quality of node feature now. So we are going to see shallow feature, language model, and large language model features. Okay, so the shallow features, so if you look at OGB dataset, so they have already designed some nice handcrafted features for each dataset. For example, this is skipgram for OGB archive. And what happened is that you get 70% accuracy on the test set in only 4 minutes. Okay, so this is very fast, and I think this is a very good baseline for model performance. Now, as I said before, the state of the art is GLEM, and GLEM was training simultaneously a language model, okay, and also a GNN. And basically, this model got the best, accuracy of 76.5%. But of course, because you need to train, your language model, this is going to take more time. So it's going to take, 9.2 hours. Okay. So there is here at that time before the introduction of ChatGPT, that was really a huge trade-off between, if you want to increase your accuracy, you need to pay the price of, much more computational, hardware, but also training time. So now this is what we suggested. Basically, we use this LLM, we prompt them, we translate into vectors, and then we fine-tune. So accuracy was 75%, and only 3 hours to do that. So interestingly, once we published the paper, so we got at the top one of the leaderboard, and then there was other techniques that used the same approach, of course, a little better. And then now the top 3, even today, actually, I was surprised. I looked at that recently. So even today, the top 3 models for OGB archive are basically based on this tape technique. Okay, So of course, one reviewer number 2 say that, oh, we cannot trust your results because OGB archive is part of the LLM training data set, so we cannot trust you. So what we did basically is that we produce a new OGB archive, not OGB archive, but an archive data set. We called it Tape Archive 23, so it's available to download. We have 77,000 papers, same number of classes, and basically we have the same conclusion. There is nothing that changes when we do that. And again, this is also the reason that an LLM is, even if it has seen, the test set, is not able to reason very strongly with graph structure. So you still need the GNN to use the topological relationship to make good prediction. We did some ablation study. What we observed is that there is no specific feature which is better than the others. It's actually the combination which is important. So intermediate conclusion for this work. So basically, we can use the LLM knowledge and its reasoning abilities to enhance the node features of the tag and also the make it to fine-tune to the specific task. Okay. So what we did is something like is not end-to-end, so we don't train everything together. It's actually we first generate good features, and then we train the GNN. So this is, I think, along the trend now of LLMs. So basically, LLMs is not trained end-to-end. They are like 4 steps: self-supervised, fine-tuning, reward model, and finally reinforcement learning. Okay, so each step is done independently because each step is very clear to do it, to train, and I think it's very stable. And this is exactly the same conclusion that we have here. We can make it very stable and it's efficient. Everything which is stable will have better performance usually. Okay, and also something interesting is that we can leverage both actually proprietary and open source LLMs. So we have the best of the two worlds. It's also, of course, some people will like it. It's interpretable because you can see the reasoning, words of the LLM. Okay, so now let me go to the second technique that I want to introduce. This is called G retriever. And the idea is, as I told you before, is that LLM is very powerful. It knows everything. But the problem is going to make errors because we never have a good prompt in some sense. So we need to constrain, to regularize, the LLM response into a much smaller space. And to do that, actually, we are going to use, a tag, a text attributed graph, like a knowledge graph, and it will force the LLM basically to answer related to this tag. Okay, so the key question is, of course, how do we extract pertinent information from a graph and to force the LLM to be more focused? Okay, so to do that, we are going to use the tokens. So I think now everybody understand that. So because of the transformer architecture, what is very nice is to work everything as an input, right? So the input of your LLM can be, of course, your query token, but it can also be other information like visual tokens and also graph tokens. So this is what we're going to do here. We are going to use 2 kinds of tokens. So the first one will be, and I will explain that in the following slides, a graph encoder token, which is going to be here, and then a text-based token, which is going to be here. Okay. So the graph encoder token is something very natural. For example, if you do molecular science, you want to represent your graph as one vector, and then you use this one vector to make a prediction for the property that you want. So here this is the same idea. So we can select any favorite GNN. We apply multiple graph learning layers to compute a very deep node hidden feature. You compute then the mean over the nodes, and then you apply an MLP, a small MLP on that. So this way you will have a graph encoder token that summarize your topological graph and also the feature on your graph, and with one vector. Okay, so this is going to be this guy of D dimensions. The other thing, of course, is that an LLM wants to use word tokens, right? So the information, the way it processes information is by using words. So we need to, if you want to have access to tap, to the knowledge of LLMs, we basically need to transform the graph and its feature into a sequence of natural language tokens. This is important to do that. And so, for example, here you have a graph, and you can represent this graph by some textual representation. For example, a graph G is a set of directed edges defined by ij, where node I points to node j. So here the graph G is defined with edges 0, 4, 1, 6, and so on. Okay, so you have a one-to-one mapping between this mathematical representation of the graph and this text representation of the graph. However, there are many ways to use language to represent graph. So for example, in this paper, they have this nice example to show, oh, you have many representations. So the text-based representation of a graph is not unique. Okay, so this can be an issue. The other one is also what I say is not text equivalent. Okay, it's not text equivalent in the sense that if you change, this guy by this guy, you will have probably different results. Okay, so we want to have some kind of equivalence for the text representation, but we don't have it. The other thing is a scalability issue when you want to represent a graph with text. Okay, so if you take an open source LLMs, the context window is limited, right? So for example, if you use the one that we use in academia, Llama 2, so basically this is 4,000 tokens of limitation. So if your graph is small, no problem. But if your graph is, for example, the Wikipedia graph, then this is like a huge number, of nodes and huge number of edges. So this is not something that you can do. There is a scalability issue. Of course, LLMs are prone to hallucination. So for example, here we have an example that an LLM can produce nodes and edges that do not exist actually in the knowledge graph that we use. So if in the vocabulary of the graph, we have some, for example, here the one deer doesn't exist, and is still, it's part of the vocabulary. So the LLM can give you actually this entity here, which doesn't exist. So what we propose is basically, so first we are going to apply a graph RAG that I'm going to explain how we do that, to retrieve a subgraph from possibly a large text attributed graph, which is going to be relevant to the query of the user. Okay. Step 2, we are going to concatenate the user query, but also the graph encoding token and the text-based graph tokens to create the input sequence of the LLM. Okay, then step 3, the LLM will give us, will generate an answer. Step 4, we will train everything. So we will simultaneously train the GNN parameters, and also we'll fine-tune the LLM parameters using LoRa. And the good thing is that you see, if you use LoRa, you're only using 0.5% of 7 billion parameters, so it's only 35 million, and the GNN has something like 5 million. So it's not that much actually to train. So this is something we can do in academia. So the graph RAG that we propose, so this is a graph retrieval augmented generation. So RAG is today very popular. Here we want to extend to graph. The main problem is, of course, the scalability. So I'm going to tell you how we solve this problem. So yeah, let me maybe go here. So the first thing is to do indexing. So what we do is that we're going to have a text attributed graph. So we're going to take the node feature. So this is the text node feature. We have also the edge feature, the same. So we will apply a pre-trained and frozen large language model or small language model. So at that time, we just use a small language model. But we can use a large language model now. So you do that, and you get some d-dimensional representation of all the nodes and of the edge. Okay, and you store them in a database, in a graph database. So today we are lucky. There are many open graph databases that can be used. So, for example, PyG, DGL, but also Llama, Index. Also, there is Microsoft and Nebula Graph. There are also some proprietary graph database like Neo4j. Okay, so we do that. So we take this and we have vector presentation of the node and the edges. Okay. The second thing is that we are going to do retrieval. So given a query from the user, we will represent to the query, for example, what is the name of Justin Bieber brother. So we will use the same, language model to represent the query as we did for the node and the edges. Okay. And then what we will do is basically we just do a similarity metric evaluation. So here we just use a cosine metric, and we can retrieve this way the top k nodes and edges from the graph database. Okay, so we will get something like this, which is a noisy, I would say, subgraph. And then the next step will basically to extract just a smaller graph which has the most relevant information, and that's it. Okay, so the way we do that, we are going to solve the price collecting Steiner tree. Okay, so the price collecting Steiner tree is basically a tree. So if you start from this original graph, and then each node has a price. So the higher the price, the more important you want to be in the tree, in the final tree. So you can solve, you want to maximize the price, but also you don't want to take everything. So you are going to have a penalty with the cost of the solution that you want. So usually this is, you don't want to, or it should be minus, I'm sorry, it should be minus here. So you don't want to take too much nodes. So basically this is the number of nodes that you have here. Okay, so when you solve this combinatorial optimization problem, which is NP-hard, but you can have an approximate solution using semi-definite programming SDP, you will get something like that. Okay, so this is a directed tree, and you see that the directed tree usually has some kind of root node, and it flow out, for example, and of course he wants to take the larger nodes. Okay, so this is the original Steiner tree. We can modify it because here there was only the nodes. But of course, when we do graph learning, there is also the edge feature that we want to use. So we can incorporate, you can easily incorporate edge information. Okay, so we have a price also for the edge. So you see, this is, for example, an edge which is more important than this edge here. And we just, modify a little bit the combinatorial optimization problem here. And we can solve it, using a very fast technique. So this is very neat. The approximation is linear, is the most linear time approximation. Okay, so if we compare the standard RAG with the graph RAG, so the standard RAG, basically you will have your knowledge database, and then you will extract, the number of relevant documents that you want. For the graph RAG here, so we have also a graph database, and we are going to extract a much smaller but very relevant graph related to the query of the user. Okay. So now I'm coming back to the tokens of the input LLM. So the first one, again, this is the graph encoder tokens. I already talked about this. So this is, an MLP on the mean of the node, the node hidden feature at the last layer of the GNN, and it's going to be here. So this is something, of course, if you have learnable parameter here, everything can be changed, by backpropagation. So for the text base, basically we will have two sequence of input words. So the first one is the query of the user, what is the name of Justin Bieber brother, and the second one will be the textualization of the graph. Okay, so this is something again that is important for to use to tap the LLM ability. Okay, so we do that. So we have the graph representation. It will go through the text embedder. So any LLM has this first layer that is doing to do the word embedding. Okay, so here token embedding, and then it will go through the LLM. So the training is very standard. So we give these input tokens. We have the transformer layers, and then the system we generate recursively the response, because we know the label using a training set, we can basically fine-tune the system to give us the right answer. Okay, so we can, again, we are going to, compute the cross-entropy loss with respect to the generated answer and the ground truth. And then we are going to do the backward pass to compute the gradient and then update the parameters of the system. So for GNN, but also for the LLM. Okay. So in summary, GRetriever is composed of 4 steps. So we have graph-rag, which are this here, which is for subgraph retrieval related to the query of the users. Then we have a computation of graph tokens using a GNN. We have also, response generations once we go through, the input tokens and also the transformer layers. And finally, model training. Okay. So here we try to combine, the best of all worlds together. And I think this is done in a very natural way. We have to change the existing data set and create a new benchmark to evaluate this, this task. So doing the reasoning of text attributed graphs. So we have different things, explanation graphs, scene graphs, and web QSP. So the main results are basically that, here there are many things, but you should only focus on that. So if you do our technique GRetrieval, basically you will be able to beat, if you only do LLMs, so you have your LLM, you query, and then you get the answer. If you do only the GNN prompt tuning, so we still do better. And if you only do the LoRa fine-tuning LLM, so we still do better. Okay, so this is really trying to combine the best of these worlds. Okay, so the scalability is basically now we are able to, for example, only use, reduce by 83% and 99% the number of, the number of tokens, the number of nodes that we use. So instead of taking, the whole Wikipedia graph, we will only take, a very small subgraph of the Wikipedia network. Yeah, of course, the one that we were interested in is, does it improve hallucination? So we compare with the baseline, which is just doing LLM with query, and we manually. So what we did is that we asked, 100, we did 100 queries and then 100 responses, and we look at manually if there is some missing nodes or adding wrong nodes, and the same also for the edges. And we see that if you use GRetriever, you really reduce the hallucination. Ablation studies. So what we observe basically is that, and that was very interesting, is so the token given by the GNN and the tokens, the text tokens of the graph, they are actually contribute equally. Okay, so the information coming from the GNN and the information coming from the text and the LLM of the graph is they are basically both important. Okay, so they are complementary, they really improve everything. So I think it makes sense, of course, because you have your GNN, we know that they are pretty good for extracting graph information, but also the LLM has a very strong capability with text representation. So the two are complementary. So in conclusion, if we want to unlock the LLM capability, we need to use graph as represented as token, as words, but actually combining everything. So the LLM, the GNN, and the graph-rag provide superior performance. So it's not only the LLM capability that does the work, it's actually many others. So graph-rag is effective, efficient, and mitigate LLM hallucination. So here are the paper, the code, and I really invite you to read the blog post by Xiaoxing He. So she has done a terrific work here. She's the main researcher in this project, and she received for this actually the 2024 Google scholarship. So I really invite you to read a blog post if you want to have a high-level introduction of this. So also the PyTorch geometric team, they included the GRetriever, so this is very nice. And I think also something which is very interesting is to look at, again, we always go back to the question, can we use GNN to improve products, right? And I think here there is an opportunity. So if we look at the history of web search engines, so everything starting with, Google PageRank, they didn't use any text processing. Then there was Word2Vec. They use Word2Vec. Then they use language model. They use also RAG. And finally, we have Gemini. Okay, so Gemini is LLM plus RAG. So LLM, if they don't know the answer, they will look at RAG when you prompt Gemini. So the next step, hopefully, would be to use GNN and some text attributed graph, knowledge graph that would be useful for web search engine. So here, what is attractive, I think, is that everything is integrated and learnable. So this is deep learning. So the next step, of course, that we are working with Xiaoxing is basically okay. So we have the text the text feature, we have the graph feature. So the last feature you want is basically doing the image, introducing the image information. So again, today everything is a transformer. So what you can do is that you can take your image, you can decompose your image into patches, and then your patch can be represented by just a vector. So this is a visual token, and then you go through transformer layers, and you back propagate also to update the representation of your the parameters of your visual transformer. And that's it. So thank you so much for being there, and I'm happy to take any question.
Thanks for the awesome talk. So if the participants have any questions, you can type those into chat or Slack. And yeah, to perhaps get us started, I had a question. And yeah, I thought like how you propose to tokenize everything essentially and fine tune with LoRa these language models is really exciting, right? Like it really unlocks multimodality. Um, you did have a slide about graph tokenization, right? And that there's no canonical order. So how do you deal with that in this work? Like how do you kind of decide how the graph is tokenized in the end?
Are you talking about this one?
Yeah, like where you'd shown the talk like a graph slide as well, right?
I'm not sure what you mentioned. Is
Right,
it
this slide, right?
this?
So is this how you kind of textualize the graph as well?
So textualization. Where is it? This one?
Yes, yeah.
Yeah. So textualization is arbitrary.
I
It's
see.
completely
Okay.
arbitrary. So I think Brian Perozzi, has his nice, paper, and this is an issue, right? So you want basically to have, as you said, a canonical representation, and there is not. Okay, so what is for the LLM that you have been trained, the best representation to extract the most information? So this is impossible to say. So not only you don't have a unique representation, but you still need to have like a word representation. Otherwise, you cannot have access to the LLM knowledge. But at the same time, you have no idea, if this representation is good or not. So this is like prompt, right? So there is no no way to know the quality of your prompt before you try.
Exactly.
So, for example, what we did, I don't know if you noticed that, but for example, there is a change of performance in the prompt if you put the title after the abstract.
Ooh.
So I think all these models, they have this issue. So the way you prompt, you're going to have very different. So here, there should be no difference, right? If you put the title before the abstract, but there is a difference. So you need to play, and this is, I was half joking when I talk about these LLMs that so they know they have seen everything. They are like, they have seen all the human knowledge. And you can ask them anything, but if you are not precise, if you don't know how to ask them the question, they will never give you a right answer. So the only way I think to bypass this is basically to get along with the non-uniqueness of the text representation, but then to fine-tune. So before, LoRa, I was quite pessimistic about this technique, and I said, oh, it's very hard, to find actually some good representation that at the end will be some vectors, and then you need to align the vectors together with the graph vectors and everything else, but you will never be able to get something good because they have not been trained this way. But if you do this LoRa, fine-tuning, then you have a way to align this vector information. So it's not perfect so far. It also doesn't make sense if you do them, at the end. Yeah, for example, let's go to the end. So it doesn't make sense in some sense, to combine the visual tokens, the graph tokens, with the word tokens, because they are very different modalities. So what you do with the MLP that you put here, you're trying to align, the visual space, the graph space with the text space. And then what you do, if here this is frozen, basically you don't do anything, you hope for the best. You hope that in this space, the alignment is good enough to give you good precision. So it's never the case. I don't think so. But there are so much parameters that eventually give you something good. But now that we can fine-tune with LoRa, then what you do is basically you force all these spaces to align. And this is why it works better when you fine-tune.
Yeah, thanks. I mean, thanks for all the details. It's always exciting to discuss research this way. So do you have time for one more question?
Yeah, sure.
Yeah, so I guess like another thing to discuss, right, would be, so if we can convince industry of the potential of these approaches, and I'm certainly excited, do you think it's possible in the future that we have LLMs which are, let's say, like more implicitly able to handle graph structured data? Here we had to fine tune with LoRa and so forth, right? But do you think like there's a possibility to have graphs as one of the pre-training modalities?
Yeah. This
And
is what the community is trying to do today, right? So let me go to the slide. This is exactly what the community is trying to do, right? It's basically, can we do some graph foundation model? So you will be able to pre-train your graph in different modalities, and then you will combine them with other modalities. What we do today is that here we are using the LLM self-attention layers, right? So but what we would like to do ultimately is to use some, so you train very powerful foundation model for graph, foundation model for vision, foundation model for text, and then you combine them using these, transformer layers for different tasks. That would be, I think for industry, that would be the best way to go. The problem is that today only LLMs has so much knowledge, parameters, so it's very imbalanced. There is no way, I think today, that we can do a product. We can be powerful with GNN only. GNN today is just a top cherry on the top in some sense. So so it's not like, we are missing data, training data. So the web is full of, graph structure data is full of that. There is no issue with that. The question is, how do you make a product that would, excite industry like, Meta, Google, and so on, that would tomorrow say, okay, let's do like ChatGPT, but let's do this for graph. So I think, because it's not clear, and also I have this, there was a Reddit at some point, someone was saying, why isn't GNN in high demand in industry? So that was a very interesting, I think, discussion. So the only today industry that likes GNN is biology.
yes,
right? So because you cannot do today LLM for biology. So the only one that can make money of that is basically biology. And so we have the Nobel Prize. So there is a huge promise that this deep learning, graph neural network, and so on, can make money. Of course, it's a promise. It's not yet there, but I think this is today where the money is for GNN. But of course, you would like to do it also for for text. There is no reason we cannot do that. But as long as we don't have like industry, I mean, we need to be, honest with ourselves. So industry drives, the AI, the big AI, improvement like GPT, right? So GPT could never be developed, in academia. So of course, academia is very important to get the ideas. Like for example, diffusion models have been developed by a PhD student in Germany, and so on. So ideas will come from academia, but scaling up and making a societal change will come from industry. So it's part of the pipeline. If we are not able to convince people to use GNN for text, so either GNN is not good enough, or we are not doing a good work, to find the right products.
Yeah. Nice. Yeah. I think this work is definitely going in that direction, right?
It's hard to
There's a
predict.
question. Yeah. There's a question from the audience.
Yeah.
So the question's as follows. For GraphRag, could it be possible that retrieved nodes and edges are mutually exclusive and don't actually form connected subgraphs? If so, is there
Mm.
methodology to ensure that the retrieved subgraph is connected?
Yeah, so this is a very good question. So I think this is completely arbitrary again. So depending on the task you want to solve. So sometimes maybe you want directed subgraph, you want undirected. There are many ways to retrieve subgraph. So minimum spanning tree is the simplest one, but they don't have any in some sense the size of the output size cannot be controlled. This is the number of nodes. So here we wanted something, with less. So I would say everything is possible as long as you know the task that you want to optimize. So here we use this one, but again, that was for us, that was directed. So that was for us. And we also wanted to have like a small size so we can quickly, do that. So we wanted something better than the minimum spanning tree. So this is why we used Steiner tree. Which is standard. But again, I think you can use different, subgraph extraction that is going to fit your objective. There is no problem with that. It just, you need a process to extract a subgraph. That's very important. And this process has to be linear time, because if you do that on, on large graph, I mean, at the end, again, we are talking about product. You want to do it, on the fly. So you want something very, very fast. That's, I think, the only condition. So, of course, a linear approximation, a linear time approximation is never as precise. But if you take enough, nodes and edges, it should be good enough, I think, for your application.
Yeah, that makes sense. Thanks for all the detailed answers. And yeah, thanks for the wonderful talk. I
All right.
think it's really exciting and like how all these technologies come together and with GraphRag, with graph vector databases, I think we're on the cusp of hopefully the kinds of breakthroughs you talked about. So
Hopefully.
yeah, thanks for the talk.
Sure.
Um,
Thank you very much again, everyone, for the invitation.
Yeah, and again, like to all our presenters for the next session, sorry for the delay. We had technical issues, and I'm gonna hand it over to Heyu, and she'll be chairing the next session of oral presentations today.
Can you make me the host? Yeah, thanks. So hi everyone, sorry about the slight delay because we started about 15 minutes late. So we will push back everything by 15 minutes. So we have 3 exciting papers to share during our oral presentation. And the first one is decomposing force fields as flows on graphs, reconstructed from stochastic trajectories, and it will be presented by Ramon. Yeah, can you share the screen, please? Sounds good. Whenever you're ready, it's all yours.
Okay, so you can hear me?
Yeah.
Okay,
And see
great.
your
So
screen.
Yeah, thank you very much for the invite. I'm going to be talking about this paper, Decomposing Force Fields as Flows on Graphs Reconstructed from Stochastic Trajectories, which is a paper in this year's Learning on Graphs. So this paper focuses on stochastic processes and non-equilibrium steady states. So in their simplest form, continuous space stochastic processes are described by SDEs or Langevin processes, which are stochastic differential equations given by some drift term F and some diffusive term D. And whilst these are the dynamics of a single trajectory, they're density dynamics. So this is the evolution of this probability density. The probability of a trajectory being at position X at time t evolves according to the very famous Fokker-Planck equation. And when the density is stationary, this means that this left-hand side, dp by dt, is 0, and then the process is said to be in a steady state. And a steady state can either be in equilibrium, so this is thermal equilibrium, or in non-equilibrium, and that depends on whether this probability flux J is 0 or not. So if this probability flux J is 0 in the steady state, then you have an equilibrium steady state, and if it is non-zero, then you have a non-equilibrium steady state. So non-equilibrium processes are very important in a range of domains, but particularly biology, because biological systems maintain themselves in a non-equilibrium steady state to avoid thermal equilibrium, where thermal equilibrium is the situation where they're no longer dissipating any more heat to their environment, and it's synonymous with death. So here are just 3 examples of biological systems that maintain themselves out of equilibrium. You have red blood cells, the outer membranes of red blood cells flickering with non-equilibrium dynamics, human brain dynamics, here illustrated with just the first 2 principal components, showing these strong fluxes in steady state, and similarly in cell movements. And these non-equilibrium processes are also the basis of diffusion models in machine learning research. So they've gotten a lot of interest recently. So I'm going to focus on what's called the Helmholtz-Hodge decomposition. So if you have some non-equilibrium stochastic process, it can be decomposed into reversible and irreversible components. So the reversible component is stochastic, and it basically is the part of the drift that balances the diffusion. So you have some noisy fluctuations, and then you have some drift that is going to maintain you on the stationary distribution. And then you have the irreversible component, which is driving this rotation around the stationary distribution. You can see that here it's a circle. So you put these 2 things together, and what you get is a non-equilibrium process on the left-hand side that clearly is evolving over some kind of Mexican hat or donut type distribution, but with a particular non-equilibrium rotation around this circle. And so if you're interested in non-equilibrium dynamics, you're really interested in this irreversible component and how to extract it. So if you limit this to the case of isotropic diffusion, so this is where diffusion is happening in the X and Y coordinates exactly, or where your diffusion is a multiple of their identity, then the process is said to be reversible if and only if the drift is conservative. So we can basically, in the case of isotropic diffusion, write F equals J over P plus some gradient flow. If J over P is 0, then F is just a gradient flow, and so it's conservative, and then your process has no irreversible component. So this is quite a nice characterization of equilibrium versus non-equilibrium stochastic processes. Now, if your process has non-isotropic diffusion, you can just change coordinates so that you're in a basis or in a coordinate system that has isotropic diffusion. Okay, so now I'm going to take a slight turn towards graphs and simplicial complexes and show you the Hodge decomposition on a simplicial complex or graph. So I'm sure you all know what a graph is, but a simplicial complex can be defined automatically by basically taking higher order simplexes from the cliques. So a set of 3 nodes that are connected becomes a triangle, etc., etc. You can define higher order complexes. Now, an edge flow or a flow along a simplicial complex is just a function defined on the edges that is alternating. So if you just give a real value for each edge, and you have this convention that if you flip the edge, you take minus that, so xij equals minus xji, then you've defined a flow on the edges of your simplicial complex. Now, these flows have this decomposition into 3 components. So you can basically decompose this edge flow x into a curling part, a gradient part, and a harmonic remainder. And this really closely mirrors the decomposition that we had for stochastic processes. So the gradient of a flow defined on the vertices basically means you have some function f defined on each vertex, and you take the difference of those to be between two vertices to be a flow along that edge. Then you have the curl of a flow defined on the triangles, and then you have some harmonic remainder. And I'm skipping over lots of the algebraic geometry here, but this is a well-known decomposition in signal processing for graphs and simplicial complexes. So if your complex is specifically a triangulation, then we know this harmonic remainder disappears. So here we have an example of an edge flow defined on a general simplicial complex, and it breaks down into these three components. And if you sum the three components, you get back the edge flow. You have the gradient, the curl, and the harmonic part. And on the right, you have specifically a triangulation. So you only have triangles, and your edge flow breaks only into a gradient and a curl part. And this decomposition has been used in many signal processing applications. Here are just two examples that I chose. You have this ocean drifter data, or you have this RNA velocity field. It's just two examples of Hodge decompositions in action. So how are we going to bridge this decomposition of a stochastic process with the decomposition of a flow on a simplicial complex? And the way we're going to bridge between the two is by considering the Hodge decomposition of a discrete state Markov process. So a discrete state Markov process tells you the evolution of some probability where you have the probability of being in some discrete state I at time t. And this is defined by this matrix of rates, the Q matrix, which basically contains all the transition rates from node I to node j. So this has a natural mapping as a graph, because you can say that the vertices in your graph are the states of your discrete state process, and transitions occur over edges. So the real key here is, how do we define an edge flow that is analogous to the drift of the SDE? So that if I decompose that edge flow with the discrete Hodge decomposition, it looks like the decomposition of the SDE with the Helmholtz-Hodge decomposition. And it turns out that the correct way to do this is by taking basically log of the square root of the ratio of these two rates, which seems like a bit of an arbitrary choice, but it's mathematically motivated because one, it is naturally alternating, so it satisfies that it's an edge flow. And more importantly, this satisfies that the Markov process is reversible and in equilibrium if and only if x is conservative, so it is the gradient of a scalar potential. And that marries up perfectly well with what we had in the continuous state. So our continuous state stochastic process is reversible if and only if f is a gradient flow, and our discrete state process is reversible if and only if x is a gradient flow. And so we're going to use this relationship to define basically a mathematical pipeline. So here's the idea. We're going to approximate a stochastic differential equation with a discrete state process that we're going to infer directly from stochastic trajectories. We're then going to decompose the discrete state process, and this is going to recover the reversible and irreversible components of the SDE directly from these stochastic trajectories. So here's our pipeline. We're going to begin with a number of trajectories, which we're just going to consider to be a point cloud in phase space. So here I've just got two trajectories, but you might have up to 100 living in some phase space. Here I've illustrated in 2 dimensions. Now we basically want to get a grid that kind of represents where our points live. And we want this to have a uniform density. So we perform furthest point subsampling, and we get this uniform density subsample. So you can see here, I've basically just picked out a uniform number of points that I can then grid in a way that that will capture my manifold or my space. So we triangulate these purple subsampled points, and what we get is with the Delaunay triangulation, which is a very standard triangulation. I've put some references here if you're unfamiliar with these techniques. But the Delaunay triangulation is a natural way for basically filling in triangles in this space. And so what we get is a triangular mesh or a grid where you have these midpoints labeled in pink dots, and you have the actual vertices labeled as purple dots. So now we want to use these as our discrete states, these triangular bins. And so all we have to do is basically follow our trajectories through these bins and count the number of transitions from each state j to I. And then the maximum likelihood estimator is very simple. It's just the number of transitions from J to I divided by the holding time in state J. And so this way you can see that I followed my trajectories around and I've just inferred a discrete state stochastic process directly from some trajectories. Okay, so what we have in this case actually is you have transitions going from the midpoint of each triangular bin to the adjacent triangular bin. But we actually want our discrete states to be vertices, not midpoints. So we take the dual tessellation or the dual triangulation, which is very natural, and a simplicial complex that basically flips so that the midpoints are now vertices and the transitions are now occurring over edges. So now we have what we wanted, which is we have a simplicial complex or a triangulation where our discrete states are vertices and our transitions in our stochastic process are edges. So all that's left to do is to define our edge flow using our maximum likelihood estimates of the transition rate, taking log of the square root of the ratio, and we have a flow that represents the drift of our stochastic differential equation on this simplicial complex. So now we can decompose the edge flow. So the discrete version of the edge flow is very simple to decompose. It's basically just an LSQR problem. And I'm skipping some of the mathematics again, but this is because the Hodge decomposition decomposes into orthogonal spaces, which basically means you can find some function g whose gradient is most similar to x, and that is the scalar potential g that solves the Helmholtz-Hodge decomposition. So here, gradient basically is going to be a matrix, a sparse matrix. G is some vector in the space of the number of nodes, and x is a vector in the space of the number of edges. And so you just solve this problem with LSQR, you get F, and then you can just recover the curling part by taking the remainder, x minus this gradient part. And so we can decompose this edge flow into two parts, the curl star and gradient of F, where curl star phi represents all of the irreversible currents in our stochastic process, and gradient of F represents the reversible component. Okay, so now we're going to try and see if this actually works with some numerical experiments. So a first sanity check is your reversible components should be even under time reversal, and your irreversible components should be odd under time reversal. So we basically take one ensemble of stochastic trajectories, in this case from a linear Ornstein-Uhlenbeck process, and we basically construct our edge flow going forward in time and decompose it. And then we do it the same, but with the trajectories turned backwards in time. And because you have the same meshes, you have the same edges, but the flow is what changes. So we can look at the correlation between the flow when it's going forward in time and when it's going backward in time. And what you get is that the gradient flow is strongly positively correlated, which suggests that it is even under time reversal, and that the curl star flow is strongly negatively correlated under time flipping, which suggests that it is odd under time reversal. So the sanity check is passed, and it suggests that we are actually capturing reversible and irreversible currents with these two parts. So as a general measure going forward of the level of non-equilibrium or the level of irreversibility, we're going to take the proportion of the curl flow over the whole thing. So basically, how big is your curling component relative to the size of the curling component plus the size of the gradient component? And we're going to see if this metric PC lines up with what we expect. So we begin with two solvable processes. The Ornstein-Uhlenbeck, which is a linear process which we know converges to a Gaussian distribution, and the planar limit cycle, which is a nonlinear process that we know converges to a Mexican hat style distribution. And these have been parameterized so that there's some parameter theta, which causes rotation around the stationary distribution. So it allows me to change how much irreversible current there is in each of these systems. So I do this and I basically can compare PC in the reconstructed simplicial complex flow to PC in the exact solution, where the exact solution is just approximated on some square grid. So I'm not exactly comparing like with like here, but the idea is that I'm looking at how much of the exact solution is curling and how much of it is reversible. And what you can see that we capture the correct qualitative dynamics, which is that as I increase theta, I'm increasing the level of curling irreversible flow in my exact solution, but also in our reconstruction. So our method is able to capture how non-equilibrium your dynamics are relative to similar systems. So these are two solvable examples, but let's consider two unsolvable or nonlinear examples in the form of the stochastic van der Pol oscillator and the stochastic Rosler attractor. So in these cases, I haven't got an exact form for the stationary distribution, and so I can't perform the Helmholtz-Hodge decomposition exactly. But I can use my parameter theta as a proxy measure for how much irreversible curl flow I have. So I do this again, and I increase theta, and you can see that in the van der Pol oscillator, I'm basically capturing quite well that as I increase theta, I'm increasing the level of curl or the level of irreversibility in my edge flow. In the Rosler attractor, I have the same behavior, but it's slightly noisier because the Rosler attractor is in 3D. So I have to use slightly larger, more coarse triangles in order to get good estimates. And so you get more noise, but the qualitative behavior is still there. You increase theta and you increase the proportion of curl in the reconstructed flow. So with these numerical experiments, it suggests that our method actually works, that we're able to capture the level of curling flow in the original data in our reconstruction. So we're going to apply it to some real-world examples. And so we're going to focus on two case studies where we know the kind of level of ground truth. So the first one is flickering red blood cells. So you can have healthy red blood cells which have some high level of dissipation, and you can have synthetic ATP depleted red blood cells, which we call passive, which have much lower dissipation. So that means they're more reversible than their active or healthy counterparts. And this is something that has been shown in real world data. Recently, it came out in Science. And then there's a result that is much older, but also well known, which is that arrhythmic or aging human heartbeats have lower irreversibility or lower curling flow than healthy counterparts. And in the first case, the data is just a univariate time series, is the outer membrane position of this red blood cell over time. And in the human heartbeats, it's a univariate time series in the form of an ECG, an electrocardiogram. So if I have these univariate time series in both the case of the red blood cells and the heartbeat dynamics, I want to basically reconstruct phase space dynamics because that's where my method is actually working. And so we just use a very simple time delay embedding into 2 dimensions where we pick tau with a very standard method, which is the first zero crossing of the autocorrelation. And so this way, I'm basically able to take my univariate time series and get some dynamics in phase space for both healthy and depleted or passive red blood cells, as well as healthy and arrhythmic heartbeats. So there's one caveat here, which is that in my framework and in my numerical examples, I assumed isotropic diffusion. So I assumed that diffusion was happening exactly in the x and y coordinates, and that d was a multiple of the identity. In real world data, you can't assume that to be true. So we have to estimate the diffusion tensor and then do that coordinate change that I mentioned earlier. So what we do is we use this formula looks a bit ugly, but it's just the maximum likelihood estimator for the diffusion in each triangle. So you follow the trajectories, and then within each triangle, you just compute this quantity where this product in the middle is a tensor product, and it gives you the estimate of the diffusion matrix in that triangle. I'm assuming that it's constant over all triangles, so I take the average, and then I change coordinates so that my data is now evolving with isotropic diffusion. And then I can apply my framework as before. And so what do we find? We find that, we find what we expected to find, which is that healthy red blood cells have a significantly higher level of PC, which is our irreversible curling flow, compared to passive red blood cells. And this is using ensemble bootstrapping. So I'm able to generate a lot of ensembles to run this on and check the significance of the differences. But you can see that we have significance at the highest level from healthy versus passive in this example. And then we have similar results with our human heartbeats. So we see that healthy heartbeats are significantly more irreversible, have significantly more curling flow than their arrhythmic or unhealthy counterparts. And this supports the previous results in the literature, but using our new kind of graph-based framework. Okay, so to recap, we developed a method that leverages the discrete form of the Helmholtz-Hodge decomposition on a simplicial complex to approximate the continuous form of the Helmholtz-Hodge decomposition on of an SDE. We validated that our approach captured irreversible currents in both solvable and unsolvable stochastic processes, and then we applied our approach to flickering red blood cells and human heartbeats to confirm that there are elevated levels of irreversible currents in healthy conditions compared to impaired conditions, either passive in the case of the red blood cells with ATP depletion, or arrhythmic heartbeats with a myocardial infarction, which is the specific disease that we were looking at here. So in conclusion, our approach breaks new ground at the interface of graph signal processing, particularly with applications to stochastic dynamics and biophysics, which is not something that is commonly looked at with graph signal processing techniques. And it prompts more mathematical work to basically look at the relationship between the discrete or graph-based form of this Hodge decomposition, which is getting very popular, and the continuous form, which is well known for both SDEs and for just functions. Functions can be decomposed similarly with the Helmholtz-Hodge decomposition. So thank you for listening. All that's left to do is to thank my co-authors. So those are my supervisors, Alain Gorielli and Renaud Lambiot at the University of Oxford, Morten Kringelbach at the Centre for Eudaimonia, and my co-authors, Paul Expert, David Beers, and Alexander Strang. If you're interested, please read the paper and reach out.
Thank you so much for the fantastic talk. Is there any question from the audience? I think we have time to take one question. I have one question to start with. I find it very interesting that you have the application in red blood cells and heartbeat. Can you elaborate on more practical usage of your model on other biophysics? Yeah. So
in terms of like practical, there's a lot of interest in non-equilibrium dynamics in biology. These are just a couple of papers from recent years. Specifically, I don't know if it has any clinical applications at this level, but it's more about the energetics and being able to capture from data basically how much energy dissipation, entropy dissipation is happening in biological systems. And this is quite difficult to do from dynamics, and there's a number of different techniques, and this is just one more in the quiver of techniques for analyzing non-equilibrium dynamics. We picked those two examples because they were situations where we kind of knew the ground truth, or there were other methods that had been used to get a ground truth, so we could see if our method actually worked. It was partly kind of validatory. There are other exploratory avenues for looking at non-equilibrium dynamics. Specifically, I do most of my work is in neuroscience, where we're looking at non-equilibrium dynamics in the brain as a signature of cognition and of consciousness.
Thank you. I think we have one quick question. How could we use this framework to perhaps understanding the diffusion generative models? Do you have any insights?
Okay, yeah, I'm certainly not an expert on diffusion models. I know that they focus on non-equilibrium stochastic processes as well. If you like, I've seen recent work from this month actually looking at the dynamical regimes that diffusion models go through. In theory, this could be applied to the output of any stochastic system, as long as it evolves in a reasonably sized phase space, a reasonable number of dimensions in phase space. In terms of diffusion models, you could apply it to the trajectories that diffusion models take. However, when you have access to the equations, it's not necessary to use these kind of data-driven techniques. So I think with a diffusion model, from what I understand, you might have access to the actual model forms, in which case you can use basically the exact decomposition, the exact mathematics, without having to go to a data-driven method.
Got it. Thank you so much again for the great talk.
Thank you. Thank you for your time, and thanks for everyone for listening.
Now we have the second presentation from Julia. The title is A Cosmic Scale Benchmark for Symmetry-Preserving Data Processing. Yeah, whenever you're ready.
Well, thank you, and thanks for the invite to speak. So hi, everyone. I'm Julia, and I'm a PhD student at MIT. And today I'm excited to present our work on a cosmic scale benchmark for symmetry-preserving data processing which was performed as part of the NSF Institute for AI and Fundamental Interactions, or IFI for short. So let's start with a bit of background on one of the flagship observations in cosmology, which is galaxy clustering. And this is where the positions of galaxies and also their associated properties are measured by cosmological surveys, such as the one shown in the image here. And cosmologists are generally interested in studying the spatial distributions of galaxies because they can tell us a great deal about the underlying structure of the universe and also about the physical processes that shaped it. And the data from these observations is usually very complex and high-dimensional. And so traditionally, cosmologists would resort to using summary statistics, like say the 2-point correlation function, which at a high level just quantifies the likelihood of finding pairs of galaxies separated by a given distance. And so while these types of statistics have been incredibly useful, they also come with the drawback of potentially losing information about higher order correlations in the data. And so this drawback motivates the development of machine learning tools that can reliably extract information from these types of surveys and process these point clouds. And besides the downstream cosmological tasks of interest, galaxy clustering data has several characteristics that make it a valuable benchmark for stress testing graph neural networks and other machine learning methods. So the first characteristic is the large point cloud cardinality, right? So most atomistic systems that you might encounter in other scientific domains where you use graph processing, like say in small molecules, only have around 10 to 100 nodes per graph. Whereas these data sets are sometimes on the order of over 10 to the 6 points per point cloud. And so this presents unique challenges when it comes to scalability. The second characteristic is the presence of information across spatial scales. Right? So on one hand, we have gravitational forces that cause matter to cluster and create these short-range correlations. And on the other hand, we also have the growth of structures that could have been initially in causal contact, but then might now be spatially separated. And this creates long-range correlations. And so this means that we need to use methods that can capture both local and global information. And finally, the third characteristic is the symmetry structure in the data. So since the universe is homogeneous and isotropic, its properties are spatially uniform. And so this means that the distribution of galaxies should exhibit Euclidean symmetry, or in other words, invariance to translations, rotations, and reflections. And so this means that this data could also be useful for benchmarking E3 equivariant neural networks. So taking all of these characteristics as motivation, our first contribution is the curation of a point cloud data set from existing cosmological and body simulations, along with an easy-to-use interface for accessing the data set. And we also introduce a JAX-based code repository called EQNJAX, which implements common equivariant neural network architectures all in one consistent framework. And finally, we systematically evaluate the performance of various graph neural networks on downstream tasks using this data set with a particular focus on equivariant models. Okay, so let's now talk about the data set in more detail. So it's derived from an existing suite of n-body cosmological simulations called the Quixote simulations. And these simulations take as input a set of 5 cosmological parameters that describe the conditions of the universe, like say the matter density or the rate of expansion. And then they follow the evolution of millions of dark matter particles in a periodic volume. And it's important to note that since this volume is periodic, what this means is that a point that's, say, on the very right edge of the box is actually very close to a point that's on the left edge. And so it'll be very important for our models to also account for these periodic boundary conditions when computing quantities like distances. And so by uniformly sampling these 5 parameters from some pre-specified ranges, we can obtain different spatial distributions of dark matter corresponding to different possible universes. And these simulations are very computationally expensive to run. And this emphasizes the need for simulation-efficient methods to extract information from these resulting data sets. And in the subset of the data that we collected from these simulations, we have a total of 12,384 in our data set. And so we next post-process the simulations to identify dark matter halos, which are gravitationally bound structures that host galaxies. And these halos are identified using an existing halo finding algorithm. And we then select the 5,000 most massive halos in each simulation to construct our point clouds. And each point in the point cloud comes with a set of node-wise features, which are the position, velocity, and angular momentum vectors, as well as the mass of each dark matter halo. And also each point cloud is labeled with a set of global features corresponding to the inputted cosmological parameters. And the two parameters that we focus on later in our benchmarking study are the matter density, or omega m, and the sigma 8 parameter, which is the root mean squared matter fluctuation that's averaged over a sphere with a fixed radius. And so, for example, here we see two example point clouds in our data set with different parameter values, and they're especially different for omega m. And in particular, we see that the point cloud with low matter density on the left appears to be more clustered than the one with larger omega m on the right. And for each point cloud in our data set, we also compute the 2-point correlation function, or the 2PCF summary statistic, to use as a baseline for benchmarking our models. And I'll discuss this quantity a bit more on the next slide. Right, so the 2-point correlation function is essentially a measure of the excess probability of finding pairs of galaxies at a given distance r apart relative to a random distribution. Right, so on the right, we see the corresponding 2PCF plots for the example point clouds. So the one on the left with smaller omega m and hence more clustering has higher 2PCF values at larger r than the one on the right. So essentially the values of the 2PCF for large r capture long range information, while those for small r capture information on small scales. And so how do we represent this function as an input into our models? Well, we can represent it as a vector by creating bins for increasing values of r, and then computing the excess probability within each bin. And so in practice, we actually use just 24 logarithmically spaced bins to construct this vector for each point cloud. And we actually use these 2PCF vectors as a baseline for our graph level prediction tasks, where we train an MLP on these handcrafted summaries, and then we compare the performance against our GNN models and test their ability to extract more information than traditional summary statistics. So let's now look at the benchmarking tasks that we consider. So the first set of tasks is graph level parameter prediction, where given the positions of the galaxies as inputs, the task is then to recover the scalar cosmological parameters that served as input to the simulation. And we focus on predicting omega m, which depends on long range correlations, and on sigma 8, which depends on short range correlations. And we additionally consider a node level task where, again, given only the positions, the task is to predict the velocity vector at each point. And this is a pretty challenging task since we're only considering the 5,000 heaviest halos in our data set. So to benchmark GNNs on these tasks, we first convert the point cloud into a graph by adding edges to the k nearest neighbors for each node. And all of the models that we benchmark are essentially versions of the same core message passing framework, which can be represented as the classic edge level, node level, and optionally the graph level update functions. And so we benchmark the following commonly used message passing architectures 3 of which are E3 equivariant. And this means that they satisfy this condition that when you apply a transformation, such as a translation, rotation, or reflection, to the input, the output is then transformed accordingly. And each of these architectures achieves this constraint differently, which I won't go into details for the sake of time. But I will say that one thing to note is that the SEGNN and Nequip both use steerable feature representations that rely on spherical harmonics. And they both use this parameter Lmax to control their maximum degree. And finally, we also compare our models to PointNet++, which operates directly on the point clouds and processes them in a hierarchical fashion. And we also found that the use of radial basis functions as edge features was actually vital to the performance of our equivariant models. And so what this does is it essentially transforms the scalar distances into a richer, higher dimensional representation by projecting the relative distances on a basis of n radial Bessel functions with some fixed radial cutoff c. And we use Bessel functions because they were also used in Nequip. Okay, so for our benchmarking experiments, we trained these models on the graph level and node level prediction tasks, for which we use a randomly sampled subset of 2048 point clouds for training, as well as validation and test sets of size 512. And the lowest mean squared error that's achieved for each task is shown in bold in the table. So looking across all 3 tasks, variant models outperform the non-equivariant GNN and PointNet. However, for the matter density prediction task that requires long-range information, none of the models beat the baseline, which is simply training an MLP on the 2PCF vector. And this is perhaps surprising since these models should be able to capture higher order correlations compared to the 2PCF, but it also is perhaps unsurprising since GNNs are known to struggle with propagating long-range information. And so we can actually probe this further by seeing which information is present in the 2PCF that is not also captured by the learned graph embedding. And so we do this by concatenating the 2PCF vector with the graph final readout MLP. And so the 2PCF becomes this additional global feature in this way. And so we do this for our best performing model, which is the SEGNN with Lmax equals 2. And unsurprisingly, since there's strictly more information being fed into the model now, the performance improves over both the SEGNN and the 2PCF individually. But we can take it a step further and only consider using parts of the 2PCF, namely the components corresponding to small r and large r. And breaking it up this way, we see that using only the small scale components does not help the omega n prediction task. But when we use the large scale components, the performance is almost as good as when using the full vector. And so this essentially verifies the fact that the missing information in our models is precisely the long-range correlations. And I think it's really nice that this data set and this type of analysis gives us an easy way to test whether a model captures the long-range information or not. And also, given the importance of simulation efficiency for these cosmological tasks, we also benchmark our models across different training set sizes, going from only 4 simulations to nearly the full 12,000. And we see that the SEGNN models in particular show better performance across all training sample sizes. And Nequip also appears to do well in both the really data scarce and in the asymptotic regimes. So just to summarize the takeaways, we have a set consisting of simulated galaxies whose spatial distribution is informative of the underlying cosmological model. And we show that both the graph level and node level tasks can benefit from the use of equivariant models, which were also found to be more simulation efficient. And additionally, the 2PCF summary statistic outperformed the GNNs in inferring a parameter that is sensitive to long-range correlations. And therefore, we think this benchmark would be a great target for methods that aim to mitigate these issues associated with long-range information preservation. So for example, it might make sense to test transformers on this as future work. And so with that, I'd like to thank my amazing collaborators and mentors, and also to plug our repo on GitHub, where you can find the link to the data set and the implementation for all of the previously described methods in JAX. So that's it from me, and thanks for listening.
Thank you so much for the enlightening talk and very interesting benchmark. There is some discussion among the audience. So one of the question was whether there is an existence of dark matter particles, but I think one of your co-authors has answered it. So we'll, I guess, if there's no follow-up question and we are short in time, we have another question about the results. So the tables show that the EGNN model failed drastically, and is there any intuition why?
Yeah, so I think that it might be due to the lack of like model capacity, like it has the fewest parameters of all these models, but it also could just be not enough time spent hyperparameter tuning. So not sure.
Yeah. So you mentioned there are two characteristics from the results. So first one, equivariance matters, and the second one, long-range information also matters. Do you have any intuition how we can tackle both by combining them together? Because I think long-range dependency is a well-studied topic in GNN community as well.
Yeah, I definitely think it makes sense to try something like a equivariant transformer. And I think we actually have an implementation of one in our repository, but due to time constraints, didn't include it in the benchmark. So I think that would be a good combination of the two.
Cool. Yeah. Thank you so much for the talk.
Thanks.
Okay, there's a follow-up question. So PointNet++ is long range, but not equivariant.
Yeah, that's right. Yeah,
Okay.
so PointNet is also nice because it processes the data in this like hierarchical way. So I think that's also something worth exploring because it seems unsatisfying to try to basically pool the node representations from like 5,000 nodes into just one vector at the end. So yeah.
Cool. Thank you so much for the talk.
Thank you.
Now let's welcome our third presentation from Xiaotian. Yeah. And the paper title is on the equivariance of graph convolution and mixup.
Okay, hello everyone. Could you see my screen?
Yes.
Okay. Yeah. Thank you everyone for attending this talk at this special time. Happy holiday at the beginning. I start my presentation on the equivalence of graph convolution and mixup. This paper was co-authored by Case, Mehta, Anytime AI, UCLA, and Rice. At the beginning, I would like to introduce the basic idea of this paper. We build a connection between the graph convolution and mixup. They are two different ways of two different technologies of deep learning, but they have some inherent relations based on our observation. Yeah, let's get started. In case some audience may not very familiar with the graph convolutional neural network, so I introduce a little bit about the original graph convolutional works. At the beginning, we have a graph. We have a target node A here, and when we do the graph convolution, actually it's do a neighbor aggregation. It's aggregate the neighbors features into A's feature. And then we do at the very original graph convolutional neural network, we just average the, maybe do a weighted average. And then we get a updated node feature for A, which highlight in the green color. The feature after aggregation is a 4, 3 here. So it is acknowledged that the graph convolutional enhance or enrich the representation of the target node A because it just aggregate the features from its neighbors. In this way, its neighbor's feature will enhance or enrich the target node. So this is why we think graph convolutional works previously. So in this paper, we found another explanation for this. Suppose we have we focus on the task supervised node classification task. At the left figure, suppose we only have a one-layer graph convolutional neural network, and we consider the label of node A here. The label is a 0, 1, 0. This is a one-hot label. The node A belongs to the second class. So this is a one-hot label, and we use this label to supervise the aggregated feature for 3 here. But for the when we consider the idea of the neighbor aggregation or graph convolution, the 4-3 or the aggregated feature is obtained from the original features of ADCB, highlighted in the orange color. So this means because we use the label 0, 1, 0 to supervise the aggregated feature 4-3, and the 4-3 is obtained by the original 4 features. So in some way, this is this also means that we use the label 0, 1, 0 also to supervise the original node features. The original node features of ADCB, orange color. So this is the basic idea of our paper. This means we use the node A's label to train node B, C, D's feature. So in this way, we think we use the target node's label to train its neighbor's feature. So this is why we think the graph convolutional neural works so well. Yeah, based on this, we have a such equivalent training data. At the left figure, this is the original graph convolutional neural network. We use a label 0, 1, 0 to supervise the aggregated feature. And we will get a equivalent training data. Actually, this data have 4 data samples. The first one is a node A with label 0, 1, 0, and the node D, the feature is a 1, 6 with the label 0, 1, 0 as well. And also this is the same to the node C and D. So based on this, we think why graph convolutional neural network works. This is because the labelless neighbors of a target node are trained by the target node's label. So this means the A's neighbor is trained by A's label. So this is why we think the graph convolutional neural network works. So based on this basic idea, we proposed our OM method. Like we build the connection between these two mix-up technology. We can say when we do the mix-up with the equivalent training data, we have 4 data samples here. We do the mix-up on these 4 samples, and we will get a updated one, the new features and the new label. We can say this is the same to the updated feature of A. So after the mix-up, the node A's feature and the labels are the same to the label after graph convolution. So this is a kind of relation between the graph convolution and the mix-up. Yeah, based on this basic idea, we propose our idea. The graph convolution is equivalent to mix-up strategy. So this is a very, I think it's a very simple idea here. This is the whole framework of our work. At the beginning, we do a homomorphic relabel which means we assign, maybe I need to introduce the graph a little bit. We have a 4 node here, and the target node is the blue node. Only the target node has a label Y0 here. At the first step, we need to relabel the neighbors, the red node and the green node, also to the label Y0, the same label to the target node. And then based on this, we do a mix up. We can say finally the features and the labels of the target node, the blue node, are the same after the graph convolution and the mix up. So based on this simple strategy or assumptions, homomorphically relabel, we call it, we build the connection between the graph convolution and the mix-up. So the main results of our paper are here. The graph convolution is a trend as well in the test time mix-up. And 2 mild and reasonable conditions, homomorphically relabel and as well the test time mix-up. I will briefly introduce this two later in the experiment parts. The previous slides, we show the basic idea of our paper intuitively. Actually, mathematically, the graph convolution and mix-up are also very similar. We can see the first 2 equations. The first line is a graph convolutional mathematical expression. We update the feature based on the target node's labels and do the average. But we use the target node's label. We keep the target node's label as the original one, and then we get the updated feature. But for the mix-up, there is only one difference. We also mix up with the labels. We also mix up Y. So this is a kind of a difference. So when we reformulate graph neural network as a mix-up, we only need to do is to relabel the neighbor's label to the target node's label, which I highlight in red in the second equations. So once we do this, we do the homomorphically relabel. We label the target node's neighbor's label to be the target node label. We will totally reformulate the graph convolutional as a mix-up. Yeah. So in this slides, we build the connection between the graph convolution and the mix-up mathematically. That's the under one condition homomorphically relabel. Yeah. In the next, I show a experimental results. It's a very simple one. Just to do a verification on what our proposal is correct or not. This is the prediction accuracy for node classification task on three data sets. It's a very popular graph data, Cora, Salisier, and PubMed. We only focus on 2 accuracy here. The original accuracy on these 3 data sets, the average accuracy, the graph convolutional neural network is 83 and something. But when we use the MLP and also with the mix-up, we get the similar results, 83 and 57. So the average accuracy on these 3 data sets are quite similar. So in this slide, we build the connection between the graph convolutional and the mix-up experimentally. And in this experiment, we show when we use the homomorphically relabel with multi-layer perceptron and versus the results of graph convolution. We only focus on the red line and the green line. The red line is the results of the original graph convolutional neural network, and the green line is the MLP using homomorphically relabel. We just relabel the neighbors and use the new data and use a mix-up on this new data and then train a multi-layer perceptron. We can see their accuracy are quite similar. The x-axis is the ratio of training data. We use different ratios of training nodes. And the y-axis is the node classification accuracies. We can see on this 4 data sets, the homomorphically relabel achieves the similar performance to the graph convolution. And also, we also propose a test time mix-up and also versus the graph convolution. The test time mix-up means like that we train a multi-layer perceptron. We train a multi-layer perceptron with the using the original data, only use the original labeled node in the graph. And then we do a test time mix-up. The test, it means we train a multi-layer perceptron, and then we use the trained weight in a graph convolutional neural network, and then do the inference. We see the results. Also see the red line and the green line. We can see the green line and the red line are quite similar. So in this way, in this experimental, we show that the test time mix-up achieves the similar performance to the graph convolutional as well. Actually, this phenomenon was also founded by some previous works, as noted in the bottom of this slides. And also, I do some experiment to investigate more on the test time mix-up, basically focus on the decision boundary. We focus on the figures in the left hand. This is the 2 classes. This is the two classes, and each point here represents 1 node. The left figure, this figure, is the results of MLP, and this figure is the MLP plus test time mix-up. We can see they have some difference here. We plotted the decision boundary for different classes. We focus on the second rows, and we can see after test time mix-up, the nodes, the representation of nodes become more and more similar. And as well for the class 0, it has a similar phenomenon. And in this way, it's made the node far away from the decision boundary. It will, in this way, it will increase the accuracy. And as well on the figures in the right hand, we have the similar results. This column is the class 1. And then this row is the results of multi-layer perceptron, and this row is the this column is the test time mix-up with MLP. So we can see it's also get the similar results. It's make the different class more far away from the decision boundary. And also in the last experiments, we combine the homomorphically relabel and the test time mix-up together. We can see the difference. We can see the results of the graph convolutional neural network and the mix-up strategy. Also in the red line and the green, in the red color and the green color, we can see combine these 2 strategies together, the results are quite similar. It's except 1 data set here. This data set is a kind of different result, but for others, it's it's quite similar, totally even the same, with different training data split ratio. Yeah. In this presentation, I presented the basic idea of our paper. We build a connection between the graph convolution and the mix-up. For more detail, you can refer to our paper. You can get it with QR code. Yeah, we do a lot of other experiments on our paper as well, and we provide some mathematical and analysis as well. Yeah, I can take questions from now.
Thank you so much for the great talk. It's a really interesting connection between graph convolution and mix-up. We also want to add on that Xiaotian's talk is our first log TMLR track oral, so congratulations.
Thank you.
There's one question: does your definition of GCN in experiments use residual connections and batch or layer norm between layers?
Oh, we don't, because in this paper we only investigated the original graph convolutional neural network. So we only use the normalized adjacency matrix and multiply the node feature, and then use a additive function. This is a one layer. So we don't use other strategies because we want to keep it simple. This is also the original formulation of graph convolution.
Got it. And do you have any intuition on how the connection between mix-up can contribute to improving GCN architecture or proposing new architectures to kind of tackle bottlenecks, for example, on heterophilic settings?
Okay, this is a great question. I think the benefits of this relation or connection is the first benefit is we can use the mix-up to accelerate the graph convolution, because originally we need to use the whole adjacency matrix. This causes a computational bottleneck. But when we use a mix-up, we only need to train a multi-layer perceptron. So this is one benefit. And for the whole heterophilic graph, you mean, right? I actually didn't do the experiment on the heterophilic graph, but you can see from the mathematical connection between the graph convolution and mix-up, we do not have an assumption the graph must be homomorphly. So I think for the heterophilic graph, we need to do more investigation and experiments. I think maybe it's extended to that kind of graphs as well.
Thank you very much again for the fantastic talk.
Thank you.
Thank you. And I think this wraps up today's oral presentation. Thank you everyone for joining, and sorry for the delay at the start. Thank you, Xiaotian, again for the talk.
Thank you so much. Happy Thanksgiving.
You too. Thank you. See you.
So, before we close,
Yeah.
I'm not sure what the best thing to do is, but I'm guessing it's better to like stop the YouTube live stream and stop the recording.